One thing we can do with probability distributions is we can calculate the expected value of the distribution. The expected value of a probability distribution can be thought of as the long-term average or mean of the distribution. What does that mean? Well, a probability distribution reflects a certain probability space, right? It tells us that if we perform a certain experiment, then we would expect, it tells us for each outcome what the probability of that outcome occurring is, right? So imagine we run this experiment over and over and over again and calculate the average, okay? If we repeat an experiment many times, over the long term, we would expect the average, or we would expect this average, okay? We would expect this number as the average. So this goes back to the law of large numbers. Now recall what the law of large numbers says. The law of large numbers. It says that if we repeat the same experiment many, many times, then the proportion of times a certain outcome occurs gets closer and closer to the theoretical probability that that outcome occurs. If an experiment is repeated a large number of times, that's why it's called the law of large numbers, is repeated a large number of times, then the proportion of times an outcome occurs gets closer and closer to the probability. To the theoretical probability that the outcome occurs. So when we first talked about the law of large numbers, we did it, the example we first gave was a coin, right? If you flip a coin 3 times, maybe you get 2 heads and a tail. Or maybe they're all heads. That wouldn't be too surprising, right? All 3 coin flips come up heads. But over the long run, as we do this experiment a large number of times, as we flip that coin a large number of times, we would expect the proportion of heads to get very close to the probability that we toss heads, okay? So how many heads we get should be about 50%, because that's the probability of getting a head. We expect, if we toss a coin, that heads will come up 50% of the time. So, you know, 10 times isn't a large enough number, but 10 million times, if we flip a coin 10 million times, then we would expect that the proportion of times we get heads should be 50%, because that's a theoretical probability, okay? We could talk about die in a similar way. if we roll a six-sided die, every face of the die has a 1 out of 6 chance of coming up. But if we only toss it 6 times, maybe 3 of those times it comes up 1, and that wouldn't be like crazy, right? Because we haven't done it a large number of times. So if instead of 6, what if we do it 6 million times? Well, then we would expect the number of the proportion of times we roll a 1 to be very close to 1/6, because that's the theoretical probability. We expect that one to come up 1 out of 6 of the times. Okay, what the expected value does is it kind of combines all this information. It is the average or the mean that we would expect if we repeated an experiment a large number of times. Okay, so there's a formula for this, and it's similar to the formula for a mean that we already have. Except now when we're calculating the mean, and we even represent it with the same symbol, so expected value, and we'll even call it a mean sometimes, so I could interchangeably use the word expected value or mean, but in this case, this mean is more of a theoretical mean. It's if I did this experiment a large number of times, this is the mean that I would expect. Okay? And it is, I'm going to add x, each outcome x times the probability that x occurs. Okay, this is actually just an extension of our old formula for a mean. Usually when we are talking about the mean of a collection of data, we weight each outcome the same. Each individual, each member of the sample has the same weight, or of the population has the same weight, 1 over the sample size or the population size, right? What we're doing here is we're just saying, well, not every member of the population, not every outcome is going to be the same. Some are more likely than others. And so we adjust it a little bit, okay? So this is our formula. Let's see this in action, okay? Quick example. And let's go back to the case where we have a 6-sided die. So if we have a 6-sided die, the possible outcomes are 1, 2, 3, 4, 5, or 6. Those are what we can roll. Okay? And the probability, well, each roll has the same probability, right? There's a 1 out of 6 chance I roll a 1, 1 out of 6 chance I roll a 2, 1 out of 6 chance I roll a 3, a 4, a 5, a 6. Okay? Now let's find the expected value of this. That is, imagine I roll this die, millions of times, and I averaged up all the outcomes I get. Okay, so first time maybe I rolled a 1, maybe the next time I roll 1, maybe I roll a 5 after that. I'm going to take all those numbers I roll and I average them up. That's going to give me my expected value. Okay, so the expected value is what I would expect that average to be. So I'm going to add up each outcome times its probability. So what does that mean? Well, my first outcome is 1. So I'm going to take 1, and I'm going to multiply it by its probability. Probability that 1 happens is 1/6. Okay? Next outcome, 2. So outcome 2, that happens 1/6 of the time. Okay, so I'm just taking x, and I'm multiplying it by its probability in each case. For outcome 3, that happens 1/6 of the time. And I keep on going until I cover all possible outcomes. Okay? And that will give us, and I won't bore you with the details, but if you throw that in a calculator, that will give you the number 3.5. So if we rolled die millions of times, we would expect the average of those millions of rolls to be 3.5. Okay? And in the long term, the average that we observe is going to get closer and closer to this theoretical expected average, this theoretical expected value. Okay? Another way to think about expected value is it's kind of our best guess of what's going to happen next. Okay, if we roll the die once, 3.5 is our best guess without being too close to any one number. Okay, it's kind of the number in the middle. Okay, let's see how we would do this in R, because we could make this a little bit easier, just like we made it easier when we were calculating a traditional mean. So let me pull up the calculator here, make it a little bit bigger. So I'm going to make two lists. I'm going to make a list of my possible outcomes. 1, 2, 3, 4, 5, 6, right? I stuck it in C because it's a list. I'm combining them into the list, and I put them in between parentheses, right? And then I want the probability of each outcome. Now, you want to be careful here. You don't want P of X, okay? Because the calculator, it's not going to like those parentheses. So since I can't add the parentheses, I'll just leave them off. So I'll just say Px, that's going to be the probability, okay? You could choose, of course, whatever name for this you want. I like to keep the names for my variables similar to what they are in the formula. So Px, what's the probability? Well, the probability that 1 happens is 1/6. Probability that I roll a 2 is 1/6. Roll a 3, roll a 4, roll a 5, roll a 6. They're all 1/6, okay? And now what I want to do is I'm going to take x times Px. That's going to multiply each outcome with its probability. So we'll multiply 1 times 1/6, 2 times 1/6, 3 times 1/6. This particular example may not be especially interesting because all the probabilities are the same, but this will also work if the probabilities are not all the same. Okay, so multiply each outcome with its probability, and then I just add them up, right? So I'm going to use the sum function. And maybe it'll be helpful to see what happens without the sum function first. If I evaluate that, 1 times 1/6 is this. 2 times its probability, it's this. Outcome 3 times this probability is this, and so on. Okay, and now according to the formula, I add them all up. So I'll stick that list inside a sum function that says add up everything in this list, the list that I get by multiplying these two other lists. And there we go, 3.5. And if you want to give it a name, you could call it mu. That's the symbol we use, the Greek letter mu. That's the symbol we use for the expected value of a probability distribution.